Okay, so today's topic is to focus very specifically on the carbonyl group right here. This right here that's highlighted in the like in the square is called the carbonyl. Essentially, it is a carbon double bonded to an oxygen. And if you guys take a look at the sheet I just gave you that has a whole bunch more of the functional groups, you might notice that quite a few of them involve carbonyls. Right, like the acid chloride at the top, 2 down from that the aldehyde, 2 more down from that the amide, 2 more down from that, the carboxylic acid and the ester below it. A few more down from there, there's the ketone. Further down from that, there's the sulfonic acid and the sulfoxide. So I'm only going to show you 3 of them, and only 1 of them are you even tested on. So we should talk a bit about the properties of this particular functional group, though. What's happening with this oxygen right here? There's 2 bonds. What's happening with the rest of it? Yeah, lone pairs, yeah. There's going to be a couple of lone pairs. What are lone pairs kind of useful for? Like, why would we occasionally need to know about these lone pairs? Anybody have any ideas? We talked about it yesterday a bit. As to a lone pair is needed for something. Intermolecular bonding, more specifically a hydrogen bond. Okay. If things have lone pairs, it increases the likeliness that they can undergo hydrogen bonding. Because that's one of the requirements. 1, you have to have the hydrogen attached to the right atom. Okay. Now, we don't know about that based on this particular structure right here because we don't know what this bit here is, and we actually don't know what the other side is going to be either. But the other requirement is it has to have lone pairs. It has to have free electrons kicking around. And so it is entirely possible that these things can hydrogen bond. So I'll come back to that a little bit later. Other things I want to point out here is that sometimes you'll see it drawn with like an R on both sides. The R just indicating that this is not something that caps the edge of a molecule necessarily. You can actually find these right in the middle of a molecule, and it can keep going in this direction and in this direction for as long as you'd like it to. Here are the 3 things we're going to do today. We're going to do aldehydes, ketones, and this is the one you actually have to be tested on, carboxylics. So here's how an aldehyde works. An aldehyde is actually a molecule that is for sure on the edge, on the very, very, very last carbon. The reason why this one stops is that you can have carbons continually going on this like left-hand side direction, but on the right-hand side over here, we always cap it with a hydrogen, meaning that the molecule is only able to travel that way. That makes sense? A ketone is very similar, only the ketone actually will travel in both directions. And a carboxylic acid is kind of like the aldehyde, in which it actually cannot keep traveling this way. It can only keep going this way with more carbons. But rather than ending with an H, we end with an OH, which is the hydroxyl group we talked about yesterday. Here's my rationale. This is the molecule I'm supposed to show you about. I'm supposed to teach you about a carboxylic acid. Carboxylic acids are made of hydroxyl groups, which we learned about yesterday, and carbonyl groups, which I'm supposed to teach you today. My opinion is, why would I teach you about this carbonyl group right here and not show you these ones here while we're talking? Does that make sense? So, like, please don't freak out that I'm going a little bit more in depth than you have to. So, aldehydes are at the end, ketones are in the middle, carboxylic acids have the carbonyl and the hydroxyl, which means it has to be at the end. Basically, how you name aldehydes, I mean, you can just use the sheet I gave you here. All you do to name an aldehyde is change the ending to Al. That's it. Change the ending to Al. Here's another thought, though. We don't usually need numbers. And the reason why we don't need numbers is because I guarantee you that it has to be on the end of a molecule, which means it's always on the number 1 carbon. So if everything's always on the number 1 carbon, why bother adding a number? It's a little redundant. This is what a ketone would look like. Ketones, you end with an O-N-E suffix. But these ones do require a number because ketones kind of happen like partway through a molecule. It's also never possible to have the number 1 because if you had one of these groups on the very, very last carbon, it wouldn't be a ketone, it would be an aldehyde instead. So I think I have an example here to work with. No, I don't. Never mind. And then we have carboxylic acids. Carboxylic acids have this double bonded oxygen, but it also has the hydroxyl group. And the naming scheme for this, do I have this written somewhere? I guess I didn't write it down somewhere here. You always end this with the phrase oic acid. It's something oic acid. So, okay, let's make up some examples. Because I don't actually think I have many in this document, do I? Very, very few. Okay. Find, actually, you know what? Find this worksheet here. Let's do a few of these ones. I'll save that one for later here. Let's just name a few of these ones first. You're right, though. I only have I do have them in there, but I only have 2. Let's try naming this one here. CH3 over to a C with a double bond to an O, over to a CH2, a CH2, and a CH3. So here's my first question for you. This is the carbonyl functional group right here. Is it making an aldehyde, a ketone, or a carboxylic acid? You guys figure that out? You want to take a stab at it? Aldehyde is if the O group is on the very last carbon. So this one's a ketone. Okay. So you wouldn't need to name this on a diploma, but just to go with it then, how many carbons are there in a row? 5. So this would be pent, and then rather than making it pentane, the ending for ketones is ONE. We just need to tell you, well, which carbon is the double bonded oxygen hanging off of? The second one. So it's pentan 2O. That's it. Yeah. Right? Like, once I show you how to name functional groups, it's like, okay, tell me how to end the molecule. And like, the rules are the same, right? Just put a number attached to it. Let's try another one. So the one next to it looks like this. CH3, CH2, then a CH. Okay, now here's a little twist. There's a Cl down here on the bottom. Then to a C, up to an O, and then down to an OH. Okay, first thought here. You would never get assessed on this because there are 2 functional groups on this molecule. Can you guys identify the 2 different functional groups? There's one right here. So that makes it a halide. And then technically this is all one functional group, although there's 2 pieces to it. Aldehyde, ketone, or carboxylic acid. Good, carboxylic acid. So how many carbons can you find in a row? 4. So the way you would name this is you would call it a butanoic acid. We never have to number carboxylic acids. And there's a reason for it. They're always on the ends. Right? Based on how they work, this carbon right here goes up to an oxygen, down to an OH group. There's only one direction this thing can spread out backwards to my left here. So since it's always on the one molecule, we never have to number it. Does that make sense? Now, that being said, this one actually threw one little twist in here. I found this on the internet somewhere here. So although you wouldn't be required to name this, we would have to account for this chlorine right here. I don't want to take a stab as to how you would actually do that if you had to do this. Where do you put chlorine when we name things? In the front of the word. So you call it a chloro. Say that loud? Yeah, 2. Because it's on the second one. That's all. So, again, I'm going to push you just a little bit beyond what diploma requirements are. CH3, CHO. Okay, this one's not really written out for us, is it? So let's try to draw it a little bit better then. CH3CHO would be, here's a carbon. We need to go to 3 hydrogens. Then we need another carbon. It needs to go to a hydrogen and an oxygen. Doesn't it seem odd that they wrote it as HO rather than OH? If they wrote it as OH, I might think it's an alcohol. But since they wrote it as HO, it probably implies that we need an H and we need just one O. How's that going to work? That doesn't have enough bonds. Cool. Aldehyde, ketone, carboxylic acid. Good, aldehyde, because it's on the end of the molecule, not somewhere in the middle. So the way you name this is, there's 2 of them, F and Al. That's it. Do I need a number? The only place it logically could be would be on the end. That makes sense. Okay. Let me try one more for you, and then maybe we'll move past here. There's one towards the bottom of the page that looks like this. Line, 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 line. Can you guys see that one? Aldehyde ketone, carboxylic acid. Good, ketone. You have the double bonded molecule, but it's somewhere in the middle. So we're going to end it with ONE, and we just need to figure out, well, how many carbons are there in a row? Looks like there's 1, 2, 3, 4, 5. So it'll be a 2. What's 5 again? Pent. Pent and 2 ON. That's it. Once you get the hang of the naming scheme, if you have this sheet of paper that I printed off out of my old chem textbook, you can probably name almost everything. Right? All you're going to do is figure out what the suffix is. Certain things go in one direction. If it has to be on the end, you don't need a number because it's guaranteed to be on the number 1. If it's somewhere in the middle of a molecule, then you would need a number for it. Does that make sense? So as I look at this sheet I printed off for you, I haven't done this in, let's see, I graduated in 2007. I took the course in 2004. I haven't done this in 12 years. Right? But I feel like I could figure this out. Look at the sulfoxide, the second last one from the bottom. That sulfoxide involves a sulfur, but it goes in 2 different directions. You see that? It's going to require a number somewhere in there. Does that make sense? Because we're going to have to indicate where that sulfoxide is. The one right below it, the thiol group, since it only bonds in one direction, it's going to have to be on the edge of a molecule, which means it's going to be the number 1. Does that make sense? So you wouldn't bother with the numbers. Does that make sense? It's pretty intuitive. Okay, the more important stuff, perhaps, than the naming, because I feel like you'll pick up on the naming fast. I need you to know the properties. Yesterday, I told you we were going to rank these things according to boiling points. Can you guys find wherever it was that we were doing that? Because we need to add to this list. So this was up here. We had the high and the low, right? What did we write so far? I don't remember. I think at the very top we wrote out like a like something like this with an OH group. And then somewhere around here, probably we did the same sort of thing, but we did maybe a bromine. And then right below it, we would have done something that has no bromine. Is that more or less what we started with? Okay, so let's see that we can figure out where to put these 3. And by the way, only the carboxylic acid is actually testable. But let's figure out where it should fit. Okay. If we were to try to draw a molecule, did we use like 4 yesterday? Okay, so I'll stick with using 4. If we use a molecule with 4, and we were to add that guy right here, that's a ketone. Or if I were to do this one right here, that one's an aldehyde. Talk about the properties. Can this thing hydrogen bond? What are the requirements for hydrogen bonds? It needs to have a lone pair. We already talked about that. It has a lone pair. That's good. But it also needs to have a hydrogen attached to one of 4 possible molecules. The hydrogen has to be attached to an oxygen, nitrogen, chlorine, or fluorine. We have an oxygen, but is a hydrogen attached to it? Okay, so these things can hydrogen bond. That being said, are they polar still? Yeah, I'd say there's definitely a little bit of polarity to this, right? There is one side of the molecule that's slightly lopsided, if that makes sense, right? If you thought of this as like a seesaw, does that make sense? It's not symmetrical. If this oxygen over here on this side of the seesaw is heavier than this side over here, right? The seesaw would tilt downwards. There's a polarity to this. So these 2 things, by the way, are typically isomers of each other. They're often very, very similar. The only difference is you're shifting the oxygen group over 1. So these guys right here, in terms of the ranking system, are going to fall somewhere in this sort of range here. They're going to be above this molecule down here, which has no polarity to it whatsoever. But they're definitely going to be below the alcohol, because the alcohol can hydrogen bond, and these guys can't. Okay, I just have one problem. I don't actually know whether or not it would be higher than the bromine or not. And I have a couple of reasons why. If it was bromine, bromine is a bigger molecule than oxygen. Does that make sense? You know what? Even as I look at the periodic table here, bromine, chlorine, fluorine, they're all slightly bigger than oxygen. So I think actually I should probably change this around and flip it so that this one right here is on top. The other reason why is that you possibly could have more than one bromine attached to a molecule, which could possibly add to its polarity. So like these ones right here are going to more or less be around the same sort of boiling points. Does that make sense? They have similar properties. We also got to talk about the carboxylic acid though, which would look like this. So 4 in a row, like that. Anyone want to take a guess as to where this one should fit? What sort of properties does it have? In a hydrogen bond? Yes. Because this oxygen has lone pairs, and this oxygen right here has lone pairs. How does that compare to the alcohol at the top of the list? Here there's the alcohol at the top of the list. That one can hydrogen bond. Anyone want to hazard a guess as to which one hydrogen bonds better? Yeah, why? 3, 4, I think actually, because it could hydrogen bond with these lone pairs or these lone pairs, these lone pairs or these lone pairs. Not only that, it's maybe even extra polar because I mean this is even more lopsided by having this extra carbonyl group right here. So if we want to rank these things, this one actually goes at the very top. I hope I told you to leave a little bit of space at the top. I hope you didn't go way too high here. But the carboxylic acid will actually go at the very, very top. Leave a little bit of space in the middle here. I guess I can give it away. This is where esters are going to go when we do esters on Monday. In terms of our ranking scheme. So in terms of from top to bottom, your carboxylic acids, they're going to be about as high as it gets. Okay. They can hydrogen bond. They're very polar. They have lots of free electrons. Carboxylic acids are very high on the boiling point list. Alcohols are next. They have the ability to hydrogen bond as well, which is fantastic. They just have fewer electrons than the carboxylic acid does. They're maybe a little less polar. We kind of put all the rest of these next ones together. We're talking about your esters, which we'll cover on Monday, your aldehydes, your ketones, your halides. These ones all essentially, all you're doing is you're taking off one hydrogen and you're putting on an oxygen or a bromine. These guys down here, they're polar, as opposed to like being able to do a hydrogen bond like these top ones. So these guys can hydrogen bond. These guys down here, they're all polar. So they're a bit lower on the list. And at the very, very bottom of the list, you have like your alkanes. Your alkenes even. If you were to have the same molecule here with a double bond. These guys down here are non-polar. Does that make sense? Okay. Let me find some of the slides I skipped, see if there's anything I should point out. Something here I wanted to say here. Yeah, this one right here. If you guys can find this a little bit. Smaller carboxylic acids are usually liquids at room temperature. Liquids meaning that liquids have, fairly reasonably high boiling points. If you have dicarboxylic acids, what would a dicarboxylic acid look like? Yeah, you'd have one on each end, right? Well, if you were a dicarboxylic acid, you could really hydrogen bond, right? Because the one on the left end could hydrogen bond, the one on the right end could hydrogen bond. It's going to be able to hydrogen bond so well that they're usually solids. That makes sense? Which means that it's got a very high boiling point if you're a solid. Usually you call it a di-something acid. So it'd be like dibutanoic acid or diethanoic acid. You just throw a di at the beginning of the word. We actually aren't required to name that in this course. We only do one. Okay, picture slide. So this is methanoic acid, single carbon, double bonds to oxygen, OH group on the other end here. Since it's a methanoic acid though, it actually has to stop right here with a hydrogen. It actually can't keep going to another carbon, because if it kept going with more carbons, then it would be ethanoic or propanoic or butanoic. One more thing I should add, a lot of these things have common names to it. Methanoic acid, when I go buy it, is called formic acid. So a lot of these things, they have like what's called the systematic name, which is what I've been showing you. A lot of them have like other formal names, which is one of the issues with how it would be nice to almost go back in time and change the naming scheme so that like everyone was working with just one name. But does it make sense? Like as molecules get discovered slowly over time in different places in the world, I call it a methanoic acid. The guy in Australia calls it a formic acid. And unfortunately, both names kind of take off. So sometimes you have to know both of them. One of the questions on your assignment actually asks you to research a couple of different molecules and find me some of the formal names for them. Do you guys have your assignment somewhere? I think it's the very first question. Yeah, here we go. Methanoic acid and ethanol, or organic compounds used in the industry. Research and stamp some of the common names given to methanoic acid and ethanol. So you guys should hopefully kind of be able to picture what they look like. Methanoic acid will be one carbon, go up to oxygen double bond, go over to an OH group, and then the other direction is the hydrogen. An ethanol will be two carbons, and then one of those carbons has an OH group. But many of these things have common names. So like if you just go to Wikipedia, I promise you, you'll find a whole bunch of them just listed there. That makes sense. What else should we talk about here? Here are some other common names for these things. Like for example, this one here is called tartaric acid. How many carbons in a row are there? Yeah, there's actually 4 based on how this one worked. There's 1, 2, 3, 4 in a row here. There's actually, these are hydroxides right here, so those are 2 alcohols. And then these guys right here, if you ever see COOH, COOH implies carbon up to oxygen over to the other OH group. So this is actually a dicarboxylic acid, also with 2 hydroxyl groups. We wouldn't name something like this in this course, right? Like we do one thing only, rather than 4. So, but they do have common names. By the way, this is citric acid. So like when you're having like I don't know, an orange, you know, and there's that citrus sort of flavor to it, this is what a citric acid would look like. There's actually 1, 2, 3, 4, 5 carbons. This is actually a branch that goes to another, and then here's actually another hydroxide group. So at some point, these things get too confusing, and we just have to give them like a common name. Okay, here's a slide about naming things. Basically, end with oic acid. Ta-da. Okay, draw me propanoic acid. What would that look like? Three in a row? Does it matter which side you do this to? No. I'll go this way here. O to OH. H, 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 H. By the way, there's not, like, there's always like a, we usually break these guys up into like a 3-dimensional, actually you guys should know the name of this shape. Trigonal planar. Remember that name? Trigonal planar? This is going in 3 directions. 1, 2, 3 directions in the plane. So don't try to put an extra hydrogen here. That'd be the most common mistake I think kids would have. Don't put that hydrogen there, because that's too many bonds. Easy enough? Awesome. Moving on. This is the one that smells, by the way. When we do our smells lab, we're gonna try to make really nice smelling things, but this is an oic acid, and it is rancid. The actual product that we make is nice. The reactants we use stink. Anyone figure out what this is called? Yeah, this is butanoic acid. There are 1, 2, 3, 4 carbons in a row. Include this carbon. So it's a butanoic acid. When you guys use this one on Tuesday, it's actually got another name. They call it butyric acid is another name for it. But that would be its like another version of its name. This stuff stinks. We're going to try to contain it as much as possible. Oddly enough, though, when you react it into something else, then it doesn't stink anymore. Then it smells nice, like raspberries or oranges or something. So that's the hope. That's all I got. That makes sense? Okay, so here's my suggestion. Try the rest of the worksheet here. These do go above and beyond the expectation you're supposed to have. Like, you're only supposed to do carboxylic acids. You're not supposed to do dicarboxylic acids, where there's 2 of them. You're not supposed to do carboxylic acids and an iodide. But honestly, like, give it a try. Like, I feel like you guys are pretty bright. Like, you'll figure it out. So try this worksheet. Other than that, kind of have the rest of the week now to just do stuff, right? So tomorrow's Flex Friday. Work on assignment, work on lab. But maybe try this just to see if you get the hang of it. Call me over. I'll mark it for you if you want. So, sound good? Sounds good. Awesome. It's actually kind of easy at this point. It's like